Guys, here's a question for you. Let's say this right now. You have some bills in your possession. Specifically, you have 10 bills. Some of them are $1 bills. Some of them are $5 bills. Some of them are $1 bills, and some of them are $5 bills. Okay, so how many bills totally? 10. You have some ones and you have some fives. There's 10 paper bills total. I'm going to tell you, you have a total amount of money of $34. How many fives and how many ones do you have? You got some fives and some ones. You have $34 total. And you have 10 bills. There's 10 paper bills you can lay down. How many fives do you have and how many ones do you have?
No, I got it.
You got it, Tori?
Yeah.
Tori, what's your answer?
6 5s and 4 1s.
Okay, reason for me.
Because 5 times, so there's $5 bills, or there's 6 $5 bills, and 6 times 5 is 30.
So if you're saying there's 6 $5 bills, that's $30, right?
Yeah, and there's 4 $1 bills.
And 4 $1 bills.
34.
So that's my total of $34. And then, if I have 6 fives and 4 ones, do I have 10 bills totally?
Yes.
So the answer here asks for these 6 fives and 4 ones. Now let me ask a question. Was that kind of hard to think about? Not too bad. There was a lot of reasoning we had to do in there and think, a lot of guessing and checking, right? So today what we're going to start looking at is situations like that. We're going to be looking at satisfying a couple of parameters within the problems that we look at. And when I talk about satisfying parameters, in that last problem, we knew that there were how many total bills? 10. So that was one thing we had to satisfy. We had to satisfy the situation where we had 10 total bills, but we also had to satisfy the idea that we had how much money totally? $34. So we had to basically say, okay, we have this many fives and this many ones, so we had 10 total bills. That was one parameter to satisfy. And then the other part of it was the amount of money had to total $34. So how many conditions were we trying to satisfy there? How many conditions were you satisfying there?
2.
2 of them. Okay, very good. 2. So this is exactly what 5.1 is going to start dealing with today. It's going to start talking about solving systems of equations. Systems of equations are going to be basically, instead of solving one equation at a time, you're now going to be solving 2 simultaneously, and I'll show you what that looks like. But our job today is to look at solving equations by, what's the process they're telling us to use right here today? Graphing. And this is going to be pretty easy, all right? Now the note I want to make to you today is this. The note I want to make to you today is this. Slope-intercept form. Will make this very easy for you today. All right, so if you can rewrite all of your equations in slope-intercept form today, this is going to make life a lot easier for you today. So my suggestion would be, if we see any type of an equation that's not in slope-intercept form, you might want to rewrite it or rearrange it such that it is in what form? And life will be a lot easier. Okay? So our goals for today, guys, is the following. Check the solutions. The solution of our problem that we just got done talking about was that, hey, 6 5s and 4 1s. 6 5 and 4 1s. That was our solution. We're going to check to see if solutions are working for systems of equations. We're going to solve systems of linear equations by graphing, and then we want to look to apply them to some real-life problems. So note-wise today, this is going to go pretty quickly today. I think we'll catch on to this nicely. So let's roll. Guys, the first thing we need to understand about what we're doing today is what is a system of linear equations, right? So I'm going to go ahead and blow this up a bit. System of linear equations. Here's what it is. It is going to be 2 equations. 2 equations with 2 unknowns. 2 equations with 2 unknowns is what this is going to be called. All right. And as an example, you might have something that looks like this. You might have y equals, I don't know, 3x minus 6. How many equations are up there? 1. In order to turn this into a system, you would need 2. Okay, so let me think here. All right. They're going to ask you to solve stuff like this right here. In other words, they're saying, find me a value for x and find me a value for y that's going to make both equations true at the same time. Okay? So the system of equations is going to be a deal where you have two equations with two unknowns. Here's equation 1. Here's equation 2. My unknowns in each are x and what? X and y. Okay? Two unknowns are x and y. All right. So let's get that. And then a solution of a system of equations is going to be the following. Solution to a system of equations is going to be the following. It's going to be an ordered pair. It's going to be an ordered pair, x times or x comma y. It's going to be a point basically that makes both. It's going to be a point that makes both equations true at the same time. It's going to be an ordered point that makes both equations true. All right, so keeping in mind, ordered pairs, whatever that first value listed, that always substitutes for which variable here, kiddos? X, and the second value in that ordered pair will always substitute for y. As an example, to the solution above right here, the solution for above right here is going to be the point 2 comma 0. And check it out with me. And I'll show you how to get this here in a bit. But check it out with me. 2 comma 0. Guys, what's 3 times 2 when I substitute x for 2? What's 3 times 2 when I substitute up here? 6. And then 6 minus 6 is what value? 0. Isn't that the y value we wanted right here? Okay, check it out here. When I throw 0 in for y and 2 in for x, do you get a true statement? Does 0 equal negative 2 times my x value of 2 plus 4? If I threw 2 in here, what's negative 2 times 2, kiddos? Negative 4. Negative 4 plus 4 more is what? 0. Golden? Good? Okay, so this point right here, how many equations do you have to make true here? Okay. Now I'll show you something here quickly. I'll show you something quickly. Again, both equations are in slope-intercept form, right? So I'm going to jump into which calculator you think? Which calculator you want me to jump into? Decimals, all right. Hey, somebody read to me the equations again. The first equation, there it is. What was the equation for the first line that we put up there in our example? Y equals what? 3x minus 6, okay? So I'm going to type this in here. Y equals 3x minus 6. Okay? Real quickly, guys, you agree that the y-intercept down here is negative 6? And then the slope through that point is to rise 3 and run 1. Do you guys agree with that? Okay, what was the second equation, kiddos? Negative 2x plus 4. Okay? What did we say the solution was to this system? 2 comma 0. Let's find 2 comma 0 over here. 2 comma 0 being that point right there. If I had to ask you guys your description, if I had to say maybe describe to me what a solution looks like graphically for a system of linear equations, how would you describe that on the graph? What is the point 2 comma 0? What's happening at 2 comma 0 in other words? It's where they meet. It's the one point that's on each line. Basically, today you're looking for a point where the two lines do what? Meet. That point where the lines meet is going to be the point that is the solution to your system. Okay? So, when we start looking at graphing stuff today, we're going to say, hey, in order to solve this right here, I need to know where these two lines actually meet or cross. All right, so let's go back to the notes here. I want to go ahead and kind of take some time to look at this example right here. This is a really good problem. We're not going to graph this at all, but rather we're going to look at how a problem like this would work, and then I want to show you how long a problem like this can be, and then after this problem's over, show you how much quicker graphing can work compared to what we're going to do. Guys, right here it says that we open a bed and breakfast. In order for us to open a bed and breakfast, how much money do we have to spend preparing a room? $600 preparing a bedroom to rent. All right. So then the cost to your family for food and utilities is $15 per what? Night. Okay, $15 per night. I'm going to go ahead and just do something here. You guys agree that $600 is like a cost to us if we're running this business, don't you? To start up, it costs us $600, right? And then how much more does it cost us per night? How much more does it cost you guys per night? So in this example right here, for us to run a business right here, it costs you $600 to start it, and then you add $15 for every night. So part A right here says write an equation that represents the cost. Well, I'm going to do this right here. I'm going to say our cost Y is going to equal the $600 to start up plus how much each night? 15. So how do I represent a cost of $15 per night being added to the original startup cost of $600? What would you add? 15 what? 15x. Okay. So this right here would be some kind of a cost function to us. This would be a cost function to us. Now in the business world, if you're going to make it in the business world, do you want your costs to be really high? Okay. There's another term that the business people use in part B. And part B says write equation that represents the, what's the word? Revenue. Revenue is the amount of money we as business owners would be bringing in. Okay? So did it cost us some money to start at first? But if I'm a business owner, over time, we should be bringing more money in than we are putting out, right? According to this right here at our bed and breakfast, how much are we going to charge per night to make money, guys? $75 per night. So an equation to represent my revenue right here would be Y equals, how much money are we bringing in each night then? Well, this is our cost. This is what we're spending, right, as a business owner. But how about as a business owner, what are we bringing in each night? Every time we have somebody there, we bring in $75 each night. Okay? So we have an equation for our cost, and we also have an equation for our revenue. Cost, how much are you spending? The revenue, how much are you bringing in? Well, part C says write a system of linear equations to model this problem. How many equations to a system? 2. How many unknowns? 2. Ugh. Haven't I kind of already written both of these right here? Wouldn't the system just be both of these put together now? This is my cost function, 600 plus 15x. There's the first equation. Second equation I wrote. There it is. Now, guys, what starts out bad for us? The cost, or I should say this, what starts out higher for us? The cost or the revenue? Whoops. Thank you. What starts out higher for us? Well, does the cost or the revenue? I guess that's the question I'm asking. Cost starts out higher. You got $600 to do that, right? So are we in the hole or are we ahead right off the bat? We're in the hole. Eventually, over time, we want to do what? Gain it all back and eventually move forward or move ahead, right? Okay. So the system's written right there, and I'm going to go ahead and move to the next page in terms of what we're talking about. And in the next page right here, they say, hey, I want you guys to complete the table for the cost and the revenue. So the system was y equals 600 plus $15 for each night that somebody's there. And then our revenue each night is 75 times the number of nights that they're there. Okay? So let's just go ahead and start this chart right here. Let's go ahead and talk about our revenue function first. Okay, our revenue function first. Guys, if we have 0 nights of somebody staying there, and by the way, which function is our revenue? The first one or the second one? Okay, so this is a cost to you. Second one is a revenue function to you. So let's go revenue first, guys. What's 75 times 0 going to be? 75 times 0 going to be 0. And then 75 times 1. How much money have you earned back if they stay 1 night? If they stay 2 nights? What would be 75 times what? 2. By the way, what kind of sequence is this? Just kept on talking about it. Starts with an A. Arithmetic. All right. 75 times 3 would be 225. I'll fill this in quickly. I'm just adding 75 each time, aren't we? 300, 375, 450, 525. I think I'm doing this correctly, aren't I? Just because I'm a math teacher doesn't mean I'm always right. All agree with that? So after 10 nights of somebody staying there, 10 nights of staying there, how much money have you brought in? $150. How much have you brought in if somebody stays 6 nights? Or if you have 6 nights of customers? 450. Okay, let's compare that to the cost values. Here's the cost values, top function. I'm going to go 15 times 0 plus what? 600. Well, what's the first value going to be? What's the first value going to be? 15 times 0 plus 600. Going to be 600? Wouldn't it be 600? If I throw 1 in there, 15 times 1 plus 600 is 615. If I throw 2 in there, what's 15 times 2? 30. So this is 630. It looks like to me this is going up by how much each time? So I'm going to fill out the table. 645, 660. Guys, do I have a profit or a loss if only 4 nights of people staying here? What was my revenue value at 4 nights? 300. What's our cost? 660. Am I ahead or behind? Behind. Okay. This will be a 675, 690, 705, 720, 735. Guys okay with the chart there? All right, so in the chart it says how many nights does the family need before they actually break even? 10 nights. The point at which cost and revenue are the same. Now what's going to happen on the 11th night then? The revenue is going to be more than the cost. So instead of having a loss on money after the 11th night, we're now going to have a profit here, aren't we? You think? This point right here though, guys, 10 comma, I want to talk about this point right here that we're at. This is really 10 comma 750, isn't it? If I had to say, hey, here's a system of equations, what point, if you would graph these, what point would these 2 lines cross at? What would you tell me? 10 comma 750. If I throw 10 in for x, that's 150, plus the 600 gets you 750. Likewise down here, if you go 75 times 10, that is also 750. So again, everything that we're looking at here for solving systems of equations, or solving 2 equations with 2 unknowns, find that point that makes both equations true at the same time. So party, what do I have to say here? How many nights does a family need before they break even? 10 nights. Okay, so let's just talk about letter F here. I'm going to go ahead and graph this here. You guys don't need to do this. I'll put the graph in nicely for us. All right, guys, right here. This would be the graph of them right there in the first quadrant. Okay. Don't worry about the graphs too much, but I just want to go up to the point of intersection on my graph right here. What do you notice about the point there? What is it? 10, comma 750. So the whole idea about today is, hey, when you graph this stuff, you want to find a point where the lines do what? Meet. That will be the solution to the system. All right? That will be the solution to the system. So in letter F, it says use Desmos to compare the graph of the model to the table. Well, we did right here, and we found that this point where the two lines meet is considered which point right here, guys? Which point is that considered? Break even. All right? So in this particular example, it says use Desmos to compare the graph of the model to the table up here. What do you notice? Well, I'm going to write this. The point, which was 10, comma 750, the point where they met, morning, Kyle. Point where the lines met was the break-even point, or was the solution, if you will. Okay, so the point where the lines met was considered my break-even point right here. The point where the lines met was considered the break-even point. So are you guys understanding what it is when I say, hey, here's a system of equations? You understand what it is that you're looking for right now? What are we looking for from now on? Okay. Point where they meet, break-even point, or a solution. The point that's on both lines at the same time, however you want to describe it. All right, so let's get started with the examples we need to make sure that we're clear on. Example 1 says, hey, I want you to determine if a point is a solution to a system. So in example 1, they say, hey, here's the point, 3, comma 7. Is that a solution to the following system? Guys, go ahead and graph those two equations in decimals for me. Why don't you guys pull decimals up, graph those, and tell me if the lines do meet at 3, comma 7. And then algebraically, I'll show you what it is that we're trying to accomplish here, okay? So get into decimals and punch those two equations in. Get into decimals and punch those two equations in. Do they meet there? Okay, so Jacob's saying when he graphed his, they meet at 3, comma 7. All right. Now another way to look at this, and this is how I want you to also look at them as well. We already know the solution 3, comma 7 is or is not going to work, Jacob. It is going to work. That's where they cross on decimals. All right. Well, if you weren't doing that and I said prove it algebraically, here's how you would do this. Guys, basically what this is saying is when you input 3, you get an output of what? 7. Or if I put 3 in for which variable? X, I have to put 7 in for Y. So let's check this. I'm going to make kind of a T-chart here. You might want to do the same thing. First equation I'm going to check is going to be Y equals 2X plus 1. So if I want to know if 3 comma 7 right here is my solution, what do I have to throw in for Y? 7. Okay, so let's do that. I'm going to have 7 equals. What are you throwing in for X given this point? Let's see. I have got 7 equals, what's the product of 2 and 3 on the right? 6 plus 1 more. 7. My comparison is what I'm looking at in the end. A value on the left, one value on the right. Does 7 equal 7? So when I insert that point 3 comma 7 to the original equation, does 3 comma 7 work for you? Yeah. It does. Okay, so what I'm going to do is I'm going to say, hey, I get a true statement here. What would happen if you got a false statement? Can that point be a solution then? If you ever get a false statement, you're done. You know the answer is no. But since this first statement is true, I have to go through and then check the second equation. Now, the second equation, standard form, 3x plus 4y equaling 37. Same game. What do you have to substitute for x again? So we're going to go 3 times what? And what's going in for y? 7. So 4 times 7. This is going to equal 37. All right, help me out arithmetically. 3 and 3, that product is 9. 4 and 7's product is? All right, help me on the left side. Combine those numbers. 9 and 28. What are you going to get? 37. Okay. True statement or false statement? Statement's true. So when I put that point in to both equations, and that point gets you to a situation where both equations are true, is 3 comma 7 a solution to that system? You bet it is. You bet it is. Yes, because the point 3 comma 7 makes both equations, what's the word? Makes both equations true. Yes, because 3 comma 7 makes both equations true. So if any time one of those equations would turn out false when you're checking to see if a point's a solution, what are you going to say about that point being a solution then? Yes or no? If any of them ever turn out false, what would you say? No, not a solution. Okay? Good. Any other questions? Everybody have that down? Next page, let's get into this then. Okay, guys, this is the part right here today where I want to make a note to you. You're not necessarily going to be drawing lines as much as you can define forms, but here's the deal. Solving systems by graphing, make this note right here. I already, guys, know that you are, but just as a reminder, you must be perfect on these. You have to be perfect on these graphs, because if you're not perfect, things aren't going to be good. Our job, we want to find the x comma y point that makes both equations true in the same setting. In other words, find an x, find a y that makes both of these true. Now, at the very beginning of the notes, I said there's a certain form that if your equations are written in a certain form, life will be a lot easier for you. What was that form? Slope-intercept form, right? Look at my 2 equations right there. Are they both in slope-intercept form?
Yes.
Are we golden?
Yes.
Okay, let's rock this. Here's what I'm talking about, graphs being perfect. In this equation right here, what's the y-intercept? 5, and then the slope to that. Be careful on this. -1. So what I'm going to do for this first one, I'm going to do this first line, and we'll do it in black there. First thing I want to do, start your y-intercept to 5. Do that. Now, this is the part where you're going to want to make sure you do your rise and run as often as you can until you completely run off a graph. So in other words, my slope being -1 would mean from the intercept from down 1 and right 1. You agree that from point to point, that slope would be -1? So you're going to continue to do that for the whole graph. Continue to go down 1 over 1, plot, 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 down 1 over 1, plot. Okay, you get it, right? Have I completely filled out the whole graph? No. What other direction should I go? Up and to the left, right? So up and over. All right. That's what it means to have a perfect plot. You've got all those points plotted there for that line, y equals -x plus 5. Okay, so what was the second part of that system? What was the second equation to that system? Y equals 2x minus 1. Again, we're trying to say what value of x and what value of y would make both of these true at the same time. I'll do this one here in, should do it in yellow. Black and yellow is good. What was the y-intercept in the second equation? -1? Yeah. I'm going to start -1. Now again, when I start there, now do your slope. What was the slope? I'm going to rise 2 and run 1. And then when I do this again, I'm going to rise 2 and I'm going to run 1. What happens right there? They're going to cross right there. And we've talked about this already today. We say, hey, the solution to the system is going to be that one point where my lines do what? They're going to cross. Okay? What is this coordinate? What comma what then up here? It is 2 comma what? Right 2 and up 3. It says when my x value is 2, your y value has to be 3. That's the point where they meet. So, if I say, hey, what's the solution to this? You're going to say 2 comma 3. Check out the first one, guys. What's 2 times 2? 2 times my x value of 2. 4 minus the 1 is 3. Works, right? If I make this a -2, what's -2 plus 5? 3. Works. The only thing you're doing is looking for the point where the lines do what? They meet. Yep, cross. All right, so let's look at one that's maybe a little more difficult. Any more time with this one here? Are you guys okay with that? Are you guys okay with that? All right, let's look at the next one. The next one's kind of tricky because I want to solve it, yes. Want to solve it, yes. But what about form? Neither one are in slope-intercept form, so we might need to rewrite these. Okay? So I'm going to rewrite these here. I'm going to kind of make a T-chart here. I like to make T-charts when I have to rewrite stuff, so I think you should do the same thing. What variable do you want to be all alone then? Y. So if I want y all alone, we have to get all the x's away from y first, or to the other side. So here's my first equation, 2x. Wow, that's a slope too. So guys, in my original equation right here, I want to move the 2x out of here. I don't like this 2x right here. So if I move 2x to the opposite side, as it's positive on the left, if I move it to the right side, what would it be on the right? Negative. Moving it to the opposite side. Change the sign. So if I move 2x to the other side, you agree that we have y equals -2x plus 5 now? Would you agree with that? Hey, is y alone in this one? So we're okay on this one here. This is what we're going to do for graph right here. Then, my second equation, maybe a little more difficult. 3x minus 2y equals 4. Want to get y all alone. So if I want y all alone, what variable do you have to get out of there first? X. Get that 3x out of there. 3x is positive on the left, so 3x on the right would be what? So when I move the 3x, what kind of y are you left with? So you have -2y equals -3x plus 4. All of you agree? Somebody have to divide everything by now so as to get wild. Divide this all by -2. Be very careful on these kiddos. Now divide everything by -2. What are the -2 is going to do on the left side here? Cancel. So y is alone. That's good. All right. Help me out here, guys. The -3 over -2. First of all, negative over a negative would be a what? Positive. I can't simplify 3 over 2, so I'm just going to leave that in fraction form and call it 3 over 2. Whoops. That's ugly. Call this 3 over 2. X minus, what's 4 divided by -2? Will be a -2, wouldn't it? Are we okay with that? So now our job is to go ahead and graph those two equations. So I'm going to come back to this right here. My job, graph this equation in slope-intercept form. So I'm going to zoom me up on this. Guys, according to this, what's the y-intercept? 5 and then slope of -2. I want to be perfect on this. So I'm going to start up here at 5. Start up here at 5. And then come down to right 1. Down to right 1. Continue to do that until you can't do it anymore. Guys, how's my first graph look? Is it okay? You're okay with that? All right, then help me out with my next graph, kiddos. Start at -2? Yep. All right. Start at -2, that's the intercept.
Up 3 over 4.
So I'm going to rise 3 and run 2. Oh my gosh, what happens right there? They meet. So my question was, given the original system, what's the solution to the system? What would you tell me? 2 comma 1 is my solution. When x is 2, your y value is 1 to make that system true. Okay? Now I've used some big fancy words. This is kind of a difficult concept at times. You get the underlying concept that the only way we're finding answers right now is simply by graphing and looking for a point that they need at right now. All right. So let me minimize this. I'll make sure you guys have all this down. When I say everybody flip to the last page, I'll know that I'm ready to move on. So I'll wait till you get everything down. Any questions so far at all, guys? Mrs. Olson, I can't believe we're going to break this group up in a week. Breaks my heart. That's what it really breaks. Anybody need more time with that? All right, last page. I love this last question. This is good stuff. This is good stuff. I'm going to volunteer to read this last example here. Volunteer to read the last example.
Me.
Go ahead.
A test is 20 questions worth 100 points. Sections of X true or false questions with 4 points each, and Y multiple choice questions with 8 points each. How many each type of question on the test?
So you have some true-false questions, right? All right. True-false questions represented by what? True-false questions represented by what? Which variable? X. To that, we're going to add some multiple choice questions, right? Multiple choice represented by the Y. So we have some true-false questions, the X value, and the Y value representing multiple choice questions. Together, those questions have to total how many questions? How many questions on the test? 20 of them, right? Okay, so my X plus my Y has to equal 20.
Oh.
My X plus my Y has to equal 20. You have X true-false questions plus Y multiple choice questions to total 20 questions. Now again, we've been looking at systems saying, hey, 2 equations, 2 unknowns. I've only written 1 equation. Second part of this says each true-false question is worth how many points? 4. So Each true-false question is worth 4 points. So what would be an expression for the amount of points for the true-false part of the test? 4x. 4x being the amount of points for the true-false part, plus you have y multiple choice questions at how many points apiece? 8. That's got a total of how many points altogether, guys? 100. 100 total points. They want to know how many of each question do you have? How many of each question do you have? Okay, so here's what I'm going to do. Down on the x-axis, I'm going to say x represented the number of true-false questions. Y represents the number of multiple choice questions. Okay? First question, gang. Slope-intercept form or not? No. Let's rewrite this so that this is in slope-intercept form. Help me get y alone on the first one. Y equals negative. Wouldn't you just have to move the x out of here to get y alone on the top one? So you're going to have y equals negative x plus what?
20.
Okay. Everybody agree with the first equation when I rewrite that? You guys okay with that? My second equation, what would you have to move first? What would I have to move out of here first to get y alone?
The negative 4x.
So, yep. So I'm going to have 8y equals negative 4x plus 100. Divide each side by 8. Okay, and what you end up with here then, kiddos, is y equals negative 1/2 x. How about 100 divided by 8? Is that 12.5? Okay, so graphically, I want to be careful on this one here. Okay? Graphically, I want to be careful on this one right here. I have an equation that's alone up here, the slope-intercept form, and I also have this equation in slope-intercept form. We're going to go ahead and graph those now. So on this first one right here, guys, where am I going to start? Where am I going to start? 20, and then there through that point, what's your slope? So down 1 over 1. Everybody agree? Yeah. All right, so I'm going to start 20 right up here, and I'm just going to keep moving down 1 over 1 each time until I get to the other end. Oh, come on. Dot, 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 dot. Okay, are you okay with my graph being perfect, first of all? All right, now the part you really need to be very careful on is the following. The next one is saying, hey, we're starting at what value? 12.5. We're starting the second one at 12.5. So I want to be really careful on this. I want you guys to be as careful as I'm going to be. I'm going to start 12.5, so I'm going to zoom up on us a little bit. 12.5 is going to be right about here, isn't it, kids? So now, how about the slope through that? Is it negative 1 over 2? Should be negative 1/2, right? Negative 1/2. So I'm going to come down 1 unit. So 1 unit down and 2 units over puts me right about here. 1 unit down, 2 units over puts me right about here. I'm going to keep doing this. 1 over, 2 down, or I'm sorry, 1 down, 2 over, 1 down in the middle there, 2 over, 1 down, 2 over. Okay, so quick question here. I go down 1, okay. I didn't have any dot that overlapped. I had no dot that overlapped. But when I did this, can you kind of get an idea where the lines might actually meet? Can you get an idea where they might meet? Describe to me the point where they might meet. Isn't it the red dot right between the last two black dots that I drew? Would this line, if I connected them right here, line up with this right here? So it looks to me like this is the point, isn't it? Isn't that the point? 15 right here. How many true false questions, guys? 15. How many multiple choice questions on this graph? 5. So it looks like to me this point being 15 comma 5. Let's see, the x value represents the number of true false questions, 15. The y value up here being 5 represents the number of multiple choice questions. So this 15 comma 5 represents 15 true false questions. By the way, what is 15 times 4?
60.
Okay. How many multiple choice questions? What's 15 and 5 add up to? 20. That's good, because how many questions were on the test to begin with? 20. 15 times 4 is 60. What's 8 times 5? Each multiple choice question was 8 points. What's 8 times 5? 40. What's 60 and 40 add up to?
100.
100. How many points were on the test? 100. We know we have to be right. Okay. Guys, the big idea today, do your graphs on a slope-intercept form and find the point where your lines do what? Very good. Any questions about this? Okay, I'm going to go ahead and stop this.